This session is about defining the geometry for a slope W stability analysis. Generally, there are 5 parts to defining a slope W stability problem. The first one is geometry, and that is what this session is all about. Defining the geometry for a stability analysis is actually quite straightforward. It's quite intuitive, and consequently I will not spend a lot of time on this here. There are, however, a few key concepts that are worth spending time on, which we will do in this session. In our Slope W engineering book, we have an entire chapter, Chapter 5, on defining the geometry, and I refer you to this chapter for more details. Everything in Slope W for defining the geometry is based on the concept of regions or polygons and points. Points are geometric objects defined by XY coordinates. Regions or polygons, or should I say regions, are simply closed polygons. Any closed polygon makes up a region. So this illustrates what might constitute a polygon. The polygon can have any particular shape, provided the polygon closes. In this particular illustration, we have 4 polygons, or regions: 1, 2, 3, 4. The water here does not form a region, and we'll see how this is handled in a little bit of time from now. To illustrate how we create polygons and draw regions, let us go to GeoStudio and open up SLP 0 True called Draw Regions. You may find the drawing appears like this when you first open the file. The first thing is to click on the All Zoom Objects button. This button zooms up the drawing such that it is the maximum exaggeration at which we can display the entire drawing and yet still see everything that has been defined. The second thing is the Snap to Grid. We can turn the grid on and off. When you define points and regions, we strongly recommend that you always have the Snap to Grid on, and this will become clearer in a little bit. You can also adjust the spacing of the grid either by clicking on the defined and default spacing, or simply type in a particular spacing that you may wish to have. So it is flexible, and that you can completely control the grid spacing. In this particular case, we're going to stay with a grid spacing of 1 meter by 1 meter. We can draw points first and then draw the regions, or we can draw the points as part of drawing the regions. Just to illustrate the feature Draw Points, we can click at where we would like to have a point to make up a region, and notice that when I create a point, that the XY coordinates of that point are highlighted here. Now it is possible at this point to actually type in a different XY coordinate, and the point would then move. Just for illustrative purposes, if I were to type in 35 here, the point will move I didn't want that, so I will click on the undo button and go back to where I was. So the point is, points can be drawn first, and then the regions can be drawn later. The next step then is to say draw regions, and if there is no point there, then a point gets created. If a point is there, then we snap to the point. And notice that when I click on the point where I started, that the region gets highlighted, and then you see here a list of the points that make up the region. Now I'm going to define the region representing the bottom soil. Notice now that when I right mouse click, the polygon closes automatically. This is quite a convenient feature, and that I think you will use a lot to close your polygons by right mouse clicking. We stay in the draw regions mode as long as we see a plus sign. Now I will define the region representing the middle soil. In this case, just for illustrative purposes, I'm going to go around the region in the counterclockwise direction, just to show that it doesn't matter which direction you go around a region. Once again, here you see the list of points that make up the region. We can actually alter this list, as we will see in the next slide. We go out of the draw regions mode with a right mouse click. So you can see that defining regions is actually quite straightforward. There are other features like taking a look at the point numbers. Rather than using view preferences, let us go draw points, and if we click on an existing point, we see the XY coordinates of that existing point. What we can also display the coordinates that go with the point. This is a user preference, and you may want to use this feature selectively for reporting to show in the reports and the drawings the XY coordinates of certain key points. I will click on my undo button to get rid of the XY coordinate, and I will click on this icon to get rid of the point labels. There are relatively few rules governing the creation of regions and polygons, but there are a few. We cannot have regions that overlap, and we cannot have regions that have gaps, so we have to be a little bit careful sometimes in how the regions are created. To avoid overlapping of regions in this particular case, where we may have a sand lens, we may need 3 regions. Region 1 and 2 would have the same soil. Region 3 would have a different soil. But all of this is necessary to avoid overlapping of regions. We can further illustrate the point about overlapping and introduce you to the verify command. Let us go to GeoStudio and open up SLP 03. File, open, SLP03. Once again, click on the All Objects Zoom button. In this case, we don't need the Snap to Grid. And now I want to introduce you to the verify command, which we can activate either through the tools command, tools verify, and we see that there are two error messages. Alternatively, we can use the verify icon. And we see that we have some error messages, and in this particular case, the main solver would not run because of these errors. We have deliberately set up this problem with these errors to illustrate some points. First of all, we have a gap. Doesn't look like a gap, but there is a gap. If we use modify objects and select point 11 and drag point 11 a small distance away, we can see that point 11 is not part of region 1, and so in actual fact, even though we cannot see it, there is a gap or there is an overlap. I will click on the undo button, go back to where I was. We can also go draw points. We click on point 11, point 10. We see the y coordinate is 10 meters. If we click on point 7, we see the y coordinate is also 10 meters. If we click on point 11, we see the y coordinate is 9.99, and as a result, the green region overlaps the pink region. There are several ways to correct the problem. In this case, point number 11 is actually redundant. It's not required. But before we remove it, let us go into Key In, Regions, and we click on Region 2, and we see that number 11 is part of the polygon list. We also notice that point 11 is highlighted in red, as are all the other points that form the polygon. If we click on region 1, we notice number 11 is missing from the list, and also point number 11 is not highlighted in red. When it's not highlighted in red, it means it is not part of the list. Now, in this particular simplistic case, we could in fact simply add point 11 to the list, tab out of the list box, and we see that point 11 is now part of region 1 and it's part of region 2. And now when we run the verify command, we see there are no error messages. I'm going to click on the undo button to get back to where I was so that I have the error messages. And in this particular case, as I've just said a few moments ago, we could in actual fact simply delete point 11 to get rid of the problem. Modify objects, delete, and we can delete the point. Now when we run verify, we no longer have any error messages. These are just a few highlights of how to define points, define regions, how to check that regions don't overlap or that we don't have gaps, and how we can modify the XY coordinates and so forth to ensure that we have a valid definition of the geometry. Another thing to think about when you define the geometry and the points is that the geometry and the point locations affect the slice discretization. Unnecessary points consequently cause sometimes to create very thin slices that are unnecessary. The point here is, though, that geometry does affect the discretization, and I will illustrate that with this simple problem here. The first thing that slope W does is finds the and exit points where the slip surface crosses the ground surface. Next, slope W goes along the ground surface and finds where there are points and makes a subsection. At each point it makes a subsection. The next step, slope W looks at where the slip surface crosses stratigraphic lines and makes a subsection. Then it goes along a piezometric line and looks if there are some points on the piezometric line and makes a subsection. Then finally it looks where does the slip surface cross the piezometric line and makes another subsection. Having done all of this, slope W finds the distance, the horizontal distance from crest to toe, L, and the average slice width is L divided by the number of slices specified. This results in an average width. With the average width, slope W then determines an integer number of slices that can be fit in each subsection that are close to the average width. So in this particular subsection there may be 4 slices. Here there may be 3 slices. Here there may be 5 slices, and here may be 1, and here 1. The consequence of this is that the slice width is not constant from crest to toe. It varies depending on the geometry. And also the second point is that the number of slices that you may have is not exactly equal to the specified number of slices. If the default 30 is used, then you may have 28 slices, 29 slices, or maybe 31 slices. All of this is intended to make sure that we get a certain variable slice width within each subsection, subdividing the potential sliding mass from crest to toe. The main point here is that geometry and points do affect the slice discretization. And at the end of this geometry section or session, we are going to illustrate what happens when we have too many unnecessary points. Another important geometric object is the green ground surface line. All slip surface must enter and exit the ground surface line. Here you see the green ground surface line. This is a very important geometric object in all of the GeoStudio products. To illustrate the significance of the ground surface line, let us go to GeoStudio and open up file SLP04. File, open, SLP04, ground line. Once again, click on the Alt Zoom button. Once again, we can turn off the XY grid. And in this particular case here, I believe the solution has already been created, and we can go to the contour or results view. And if we now go to the draw slip surfaces command, we have a list of all the trial slip surfaces that were analyzed. We can sort this list by clicking on the headings. If we click on slip number, it sorts it by the slip number. If we click on factor of safety, it sorts the list by the factor of safety with the lowest one at the top. Let us click on slip number, and then let us scroll down to slip number 98, and we see that there is an error. We can expand this column to see what the error message is. Expand the dialog box. Number 98, slip surface enters and exits beyond specified slip surface limits. We can see here that the slip surface enters the problem on the left vertical boundary, and that the slip surface does not cross the green line at the entrance point. It crosses the green line only once, which is at the exit point. So we have an error. A slip surface must cross the green surface line twice. If we now look at slip surface 108, we see that in this particular case, the slip surface enters and exits on the green surface line. Therefore, slope W considers this a valid trial slip surface. The intent, however, was not to look at slip surfaces that come out the end of the vertical part of the problem on the right-hand side. The problem is that the green surface line is going down the vertical end of the problem on the right. This was not the intent. Once again, there are several ways to solve this problem. If we turn on our points and our point numbers, we see we have point 6 and 7 that define the right vertical boundary. If we go draw, we have to go back. First of all, we have to go back to the defined view. Then we can go draw points. If we click on point 6, we see the x-coordinate is 34.995. If we click on 7, we see the x-coordinate is 35. Therefore, while it doesn't look like it, we in actual fact have a finite slope to the right vertical end, and as a consequence, the green line is drawn on the vertical end of the problem. We can correct this problem by typing in 35 meters here, and immediately you see that the green ground surface line ends now at point number 6. I'm going to click on the undo button to recreate the problem, and quite a common trick that can be done to solve the problem and alter the coordinate is to say modify objects, click on 6, drag it to the nearest grid point, and then drag it back, and you can see now that the green surface line is at point number 6, which we intended. By dragging the point away from the grid and then dragging it back onto the grid, it gets snapped to the grid, and consequently we have now solved the problem. Now if we go back and rerun this problem, then we would now see that the slip surface would not cross the green surface line twice, and consequently this would be considered an invalid trial slip surface. So in summary, The green ground surface line is an extremely important geometric object in slope W and a very useful tool for guiding what are valid and considered invalid trial slip surfaces. Surface water or submergence is handled in slope W in a special way. Slope W is formulated on the basis of the summation of total forces. Water is a force acting on a slice and therefore must be included in the force summation for each slice. To illustrate this further, let us open up SLP 05 called ponded water. If we now go to the results view and zoom in on the toe area, and go to view slice information, and we click on one of the slices close to the toe area below the slope, we see we have a water force here of 15. We see that the slice width is half a meter. And so the 15 comes about because we made the unit weight of water 10 kilonewtons per meter cubed. This distance is 3 meters. Therefore, gamma times 10 times 3 times the width of half a meter equals 15 kilonewtons, which is the force acting at the top of the slice. Notice also that the force comes into the force polygon here. The point here is that the water weight must be included in the force resolution of each slice. Water being normal to the slope, the direction is always normal to the green surface line. So if we go view slice information and click on one of these slices, we see that the direction of the force is perpendicular to the green ground surface line. In this particular case, the piezometric line is above the ground surface. Consequently, there is positive pressure here, and that is how the water weight is computed. This is an extremely important concept because the same holds true for all methods of defining the pore water pressure. If the pore water pressure should come from a seep W analysis, then slope W looks along the green surface line and says, what is the pore pressure? And if the pore pressure is positive, then slope W automatically computes the weight that arises from the surface water and includes it in the slice force resolution. Another issue in defining the geometry is what we call physical admissibility. That is, can this thing happen in real life? Here's a couple of simple cases where they are not physically admissible, at least not in the context of a slope W. The first one is an overhanging wall. If we had a slip surface like this, number one, the slip surface does not cross the green surface line twice, therefore it is considered an invalid slip surface. Generally, slope W cannot handle overhanging walls, and the reason is that if there was a slice here like this, the base of the slice would be in the air, and slope W cannot handle that particular case. The base of the slice must be inside the soil for slope W to be able to handle the force resolution on the slice. Another situation is where we have bedrock. Bedrock in slope W is a software flag that says the slip surface cannot go into this material. So that being the case, this slip surface would come down here like this, and then it would have to go vertically upwards and jump over this lip. Slope W cannot handle this particular case because if you had a slice here like this, that means that the side of the slice has forces on it that represent the bedrock, and this is not possible. Moreover, it is also not physically realistic that this could happen because the soil would have to simply lift up vertically. This is called physical inadmissibility, and it's up to you as the user to define a problem such that the sliding could actually happen in real life, or conversely, it's important that you not define a problem that could not occur in real life. So the user must control the trial slip surfaces to represent actual field slips possibilities. Here's another example. In reality, a slip surface cannot pass through the concrete here. Therefore, do not set up a problem with trial slip surfaces passing through the concrete. The urge by many users is to give the concrete an extremely high strength, thinking the slip surface will go through the concrete. It will result in a very high factor of safety and therefore will be ignored. The difficulty is that we have now a concrete, a very, very high strength slice next to the backfill with a very low strength slice. This can cause numerical difficulties, and as a result it's not always possible to get a converged solution. So it's still up to you as the user to define the trial slip surfaces such that they would not go through the concrete. Now, as a little bit of a diversion here, here's what I have called an exam question. You may want to stop the movie for a bit, and the group may wish to pause and poll the participants as to the answer to the following question. Is the factor of safety for case A smaller, greater, or equal to the factor of safety for case B? Notice that everything is the same. The unit weight of the concrete is the same. The friction angle is the same. Only the cohesion, however, is different. So for this particular trial slip surface, all else being the same, except different strength for the concrete, would the factor of safety for A be smaller, equal to, or greater than the factor of safety for case B? It is interesting the response that people give, and the answers that they give is to some degree a reflection of their understanding of the fundamentals of the limit equilibrium formulation. This is optional. You can skip over this if you like, but it is rather interesting to poll the participants in your group to see what the answers are. Another topic that is related to geometry is importing the geometry. It is possible to import DXF files. Unfortunately, this often results in too many unnecessary data points. We will see an example of this in a bit. Also, in DXF files, often the regions are incomplete, or the regions are defined in such a way that they overlap, resulting in incompatibility. So if you are going to import a DXF file, it usually requires some modification and editing of the data once it has been imported, but the option is available to you. Another way to get data into slope W is to paste XY coordinates into the key endpoints edit box. If you bring up the key endpoints edit box, and this is a rather obscure command, but if you right-click in this edit box here, this particular dialog box comes up in which you can select all the data, or you can copy the data to the clipboard, or you can delete the data. If you should happen to have XY coordinates in a spreadsheet, for example, you could paste the XY coordinates into this edit box, and then you could join the points to form and create the regions. The key point here that I wanted to bring up is that there is quite a bit of functionality in this edit box. To get at it, you have to use the right mouse click in the edit box. Now I would like to make some general comments on good modeling practice. It's not necessarily intuitive, but as a good modeling practice, it is necessary to avoid unnecessary complexity. Complexity does not necessarily mean accuracy. Unnecessary complexity can create numerical difficulties, for example, round-off and convergence difficulties. Also, if you have unnecessary complexities and you do encounter some numerical difficulties, then the unnecessary complexity makes it difficult to determine the reason for unrealistic results. I won't take the time to dwell on this here, but I would encourage you strongly to go to the folder on the Workshop Resources CD called Papers of Interest. There are two papers there called The Purpose of Numerical Modeling and No Numerical Modeling. Is it prediction or is it process? I would strongly encourage you to read these very short articles. It will give you some insight into good modeling practices, and it also will give you some insight as to the reasoning as to why we do certain designs in slope W, for example. To illustrate what I mean by unnecessary complexity, take a look at this example. This example has too much detail. There are too many points. There's 168 points. All XY coordinates are defined to 5 digits after the decimal point. And this is likely the result of importing data from a DXF file. This accuracy in the XY coordinates, or this number of significant figures, is somewhat meaningless in a slope W analysis. So what I did is I got rid of a whole bunch of the unnecessary data. Furthermore, with all of this unnecessary information, it results in 79 slices, and some slices are very, very thin. In fact, they are so thin that a bunch of slices look like a thick black line. So what I did is I removed many of the points, I reduced the total number of points to 61 from 160 some. Reducing these number of points resulted in 48 slices, and I took all the XY coordinates and rounded them off to the nearest meter. And then I reran the problem for the exact same slip surface, and with the complex geometry the factor of safety is 1.023, and with the simplified geometry it is 1.027. For all practical purposes the factor of safety is identical. This illustrates that complexity does not add to accuracy. In conclusion, and as a general principle, a numerical model should be a simplified abstraction of a complex reality. A good model should seek to not replicate all the details in a real physical world. This is further explained in those two papers that I mentioned in the folder called Papers of Interest. So if you are interested in more information on this particular statement here, then I would urge you to go and read those two papers. So in the end we have some simple recommendations on defining the geometry. Number one, keep the geometry as simple as possible. Use snap to grid when defining points and regions. Round off all the distances. Rounding distances to the nearest meter, 2 meters, or even 5 meters depending on the problem extents. There is no value in carrying large number of significant figures in the geometry. And finally, start simple and then add complexity in stages if necessary. We would urge you not to start at the very complex and then run into trouble and having to simplify the problem to sort out the issue. It is good modeling practice to start simple and then, if necessary, add some complexity later on. This brings us to the end of the session on defining the geometry for a slope W stability analysis.